So let us look at a non-atomic network routine. And first, I need to say yet another general introduction. So as I said, there is no, as we saw, there is no way to bound a general game. Even Prisoner's Dilemma, the very simple game, we cannot give a reasonable bound in general. So we need to look at concrete cases. Luckily, many important cases, which are practically important and also theoretically, because the tools which have been developed to study those cases sometimes they're also important for other applications. So many such important cases do have some nice bounds, at least some interesting analysis. So in particular, network models are amenable to such bounds. Excuse me. And we start by giving a classical example of selfish routing by Pigo. I hope I pronounced the surname correctly. So it's an example of about 100 years old, almost 100 years old. So probably he thought about either phone, but probably it was about transportation networks. So it's a non-atomic example. So it has a source S, a destination T. The cost, these are function which say how much it costs to use an edge when the total traffic on the edge is X. So the cost function depends on the traffic, and usually it says, for example, the time it takes to pass through an edge. So something we want to minimize. So the cost of the upper edge from source to destination is constantly 1, regardless of X, regardless of traffic, while the cost of the lower edge is X, exactly the same as traffic. So the higher the traffic, the more the cost. So it can, for example, model the case when the upper edge is simply a road which is broad, does not really matter how many cars ride there, but it's quite long, or for whatever reason it takes some time to go over that road. It simply does not change based on how many cars go there, at least when the number of cars for our problem. But in our problem, it does not matter how many cars go there. Now, the lower edge models a road, or can model a road, where it does matter how many cars go there, but if not many cars go there, it's very quick. So it's a very short road, but it's a very narrow one also. So its bandwidth is slow. And so there is a source and destination cost, and they have one unit of non-atomic traffic, so it simply can be divided in any way between those routes. There is no atomic player. And we want to find the social optimum way to divide that, and the social optimum way to divide that will be a way which gives the lowest social cost, excuse me. Actually, I need to write what is a social cost. Social cost is the total cost, average cost. So it's the cost of the upper edge times the total flow through upper edge plus the cost of the lower edge times the total flow over the lower edge. And so we want to minimize that. That's very simple, similar to a normal game, an atomic game. So there is one unit of non-atomic traffic. Now, we also can define an equilibrium here, and again, I have not written it explicitly, but maybe I should have. But anyway, an equilibrium is a division of flow when no amount of flow can be can profit. Imagine that any amount of flow can profit if this amount of flow can move and experience a lower cost. So the lower edge is dominant. So the unique equilibrium, therefore, in the sense I just defined, costs 1, because everyone goes to the lower edge, so the cost will be 1. Excuse me, the total flow there will be the flow 1 times the cost of 1, which is 1. So the lower, so it will be 1. So the unique equilibrium costs 1. Now, I also want to say, what does it mean that the lower edge is dominant? It means that it's strictly better to go there if there is any flow on the upper flow edge. Then on the lower edge there is less than 1, so there is a cost is strictly less than 1. So it's strictly profitable to go to the lower edge as long as there is someone on the upper edge. When everyone goes through the lower edge, the cost is also 1. But if at least some flow, any positive epsilon, flew to the upper edge, then that part of flow would still profit by, well, if all that flow went to the lower edge, it would not profit, because then the cost of the lower edge would be 1. But if less than that flow goes to the lower edge, it would profit. So the only stable state, when there is nobody who wants to change, is when everyone goes through the lower edge. And again, I've not defined this formally here, but I hope that the idea is clear. So it's a bit of an unusual example because we don't have a reasonable, non-cooperative game in a strategic form, but I think that it's clear what I mean. So the unique equilibrium cost is therefore 1. Now, what is the optimum average cost flow? So we need to optimize to minimize the following cost. The cost of the average cost of the lower edge. So there is some x through the lower edge, and that is x times the cost, which is also x, because the cost of x is x. So that's x squared plus there is some cost through the upper edge. That's the remaining cost 1 plus x, the remaining flow 1 plus x. But the cost is always 1. So it's 1 times 1 minus x. And that is x squared minus x plus 1. That's an so-called smiling parabole, which has an unique global minimum. But we even can check this from scratch. So the parabola obtains its global minimum at the point where the derivative is 0. So that's the derivative is 2x minus 1, and the derivative is 0 when x is exactly when x is half. So when the flows are equally divided between both edges, and it's a local minimum since the second derivative is 2, which is positive, so it's a local minimum, and therefore it's one local minimum, and from there it goes on up, so that's also the global minimum. So we found the global minimum, that's where the flow is equally split between two edges. Please pay attention, that's definitely not, as I said, it's not an equilibrium. So any small unit of flow on the upper edge experiences the cost of 1 times the flow, but the cost itself is 1. Now on the lower edge, the cost is half. So it's not stable, but the average cost will be optimum. And what it will be, so when x is half, we can substitute half to the formula for the total cost, total average cost, and that would be 3/4. So the price of anarchy or the price of stability, here you have only one equilibrium, so that's the same, is as analogical to what we defined for a strategic form game. The optimum cost in an equilibrium, the cost in an equilibrium relative to the optimum cost. So an equilibrium costs 1, we've calculated that before, here, 1, here, while the optimum cost is 3/4. So the ratio is 1/3, it's 4/3. That's the price of anarchy. Even in this simple example, you have this, I guess, non-trivial price of anarchy. That's probably one example why the example is famous. And now in a general selfish routing game, the network can be arbitrarily large. It can be an arbitrarily large undirected network with arbitrary source and destination. The cost functions are arbitrary, non-negative, continuous, and non-decreasing. That's what we have to have. So the costs can be negative, cannot be negative. They depend continuously on how many infinitesimally small cars go, so how much flow goes through the edge. And of course, the more flow goes, the more flow there is, the higher the cost is, or at least it does not decrease. And then, actually we can prove, and we will prove if we have time, that the price of anarchy is actually always the same as the price of stability. In a certain way, there is only one equilibrium flow. It's so-called, there is only one essentially one equilibrium flow. So practically we can say there is one. And moreover, if we assume that all the cost flows are affine, so that means that they are all A times the cost plus B for some constant, then the price of anarchy equal to stability is at most 4/3. So the price of anarchy and stability, which we have in this simple Pigos example, is actually the worst possible which can be. Of course, proving that it's the worst possible which it can be is not trivial. So that's actually something we will prove if we have time, but that's something not trivial. Okay, so that's one example. And one important notation notice is that without limiting the cost functions, and limiting in the sense that limiting the set of possible cost functions, without assuming that the cost functions are of some form, if you only assume that the cost functions are arbitrary, non-negative, continuous, and non-decreasing, then we can find examples of arbitrarily large prices of anarchy, and stability is the same. So that's actually also an important thing. And I hope we may see such an example on the tutorial. Okay, so that was one application. Another application is that we design a network. So in the first application, we needed to move some flow through a given network. Here, we need to design a connection to connect a network. So it's a so-called network design, a network formation game. And let us define the so-called Shapley network design game, which is named after the famous scientist Lloyd Shapley, as follows. So the game is on a directed graph. It's actually a real game in the sense that we have defined before. So it's not like what we did, that it's not really a game in the formalism, but it's a real game. So H is endowed with a fixed capacity. There is a finite set of players, k players, and each player I is endowed with some source and a source and a destination, Si and Ti, in the set V of the vertices of the graph. now player I needs to connect the source to destination in a direct path, which a directed path from Si to Ti. Look at this as a set of edges, and it's a subset of E of the edges of the graph. So the strategies are all the paths of the directed path from Si to Ti, and the cost, so it's not a utility, it's a cost game of player, is the total cost of all the edges in her path. The total, not the total cost, but the total share of her cost, because for each edge, player pays the cost incurred is the cost, the fixed cost, over the number of users of that edge, where the number of users is simply defined as the number of players whose strategy includes that edge. Again, we look at the strategies as sets of edges, of direct edges, of arcs. Okay, so there is a game. The players, each one has a source and destination. They need to connect those. The set of strategies of a player is the set of direct paths looked at as a set of edge of arcs. The cost is defined as the sum of the cost of the cost shares over all the cost or edges in the path. And let us look at an example of sharply network design. So let's look at a simple example. We have k players. They share their source and the destination Si and Ti. Excuse me, Si for every player is S, and for every player the Ti is T. Now the constant cost of the edges are as follows. The upper edge costs k, the number of players, and the lower edge costs 1 plus epsilon. Epsilon will be small enough for our goals, which we will see soon. So that's the game. So the players, the strategies are, of course, every player can choose at least exactly one of the edges. That's the path. And the player pays either the whole cost of the path if she's the only player to choose that path, or half of that cost if both players have chosen that path. Okay. So now consider k players. Excuse me, that's something we just said. So let us find a socially optimum profile. A social optimum profile is, of course, if everyone uses the lower edge, because epsilon is smaller than 1, so it's in particular true that 1 plus epsilon is smaller than k. We assume that k is at least 2. So then every edge player uses the lower edge. That's a social optimum profile. And that's also an edge equilibrium, because no player would, of course, benefit from unilaterally paying more. So it's definitely better to pay half of 1 plus epsilon than paying all k. So that's an optimum profile, and that's also an edge equilibrium. So price of stability is 1. Now what is the price of anarchy? Excuse me. Now the interesting thing is that the profile where every player uses the upper edge is also an edge equilibrium, albeit a much worse one. It's the worst one, of course, because why is it an edge equilibrium? Because no player wants to pay 1 plus epsilon. I think I've said that I made a tongue slip. So I've said that it's better to pay half of 1 plus epsilon than k. It's not true. It's not half because there are k players. It's 1/k of 1 plus epsilon. It's better to pay that than k, because even 1 plus epsilon itself is smaller than k. Now that's why the first profile we looked at, when everyone plays lower, is an edge equilibrium. Now Then look at the profile when everyone plays alpha. It's better to play 1k of k, which is 1, than playing 1 plus epsilon by unilaterally deviating. So that's also a Nash equilibrium. Now, why is it the worst possible Nash equilibrium? So why is it actually the worst possible? That defines the price of anarchy, of course. Because there is no other equilibrium when at least one player plays the upper edge, because then that player would definitely benefit to go to the lower edge. Only when k players go to the upper edge, does no one benefit from deviating to the lower edge. So all the other equilibria will have everyone playing the lower edge, and that would be actually the other equilibrium. So there are only two equilibria here, because as I said, I repeat, a profile when you have less than k players playing the upper edge is not an equilibrium, because then it's better to play at most one half of 1 plus epsilon, so to join the other player, at least one who already plays the lower, than playing at least k or k minus 1. Especially remember that k epsilon is small now. So the only other equilibrium, and that's the worst one, is when all players play the upper bound, and then we conclude that the price of anarchy, therefore, is the worst total cost k when everyone plays the upper edge over the optimum total cost, which is 1 plus epsilon. So the price of anarchy is bad. The price of stability is optimum. It's good. It's 1. So there is a bad equilibrium. It can be arbitrarily close to the number of players, the price of anarchy. But the price of stability is 1. Is it true for every Shapley network game? No. It can be that also the price of stability, so the best equilibrium is bad. For example, look at this example with harmonic price of stability. Let us now look why is it harmonic. Now, look at this example. We have a k player. Player I has the same sync t as everyone else, but they have, each player has her own source, S1, S2 till Sk. So a player can choose among two roots from Si to T, either directly, and then player K pays 1 over this K. Exactly, excuse me. Player I plays 1 over I, pays 1 over I, or a player can go to V and pay nothing, and then go using this additional edge directly from V to T and play Y plus epsilon. And then she plays 1 plus epsilon over the number of players who have used this way. First to V, and then this common edge from V to T. And now the social optimum, so the social optimum profile is when everyone plays first going to V and then going to T. Because then the total cost is 1 plus epsilon. It's definitely better to pay 1 plus 1 half plus because epsilon is small enough. And it's definitely better to pay 1 plus epsilon and some other players going directly and paying something else. So that's the social optimum cost, 1 plus epsilon. Now this is, however, not an equilibrium, since in any profile, the strategy, the path going directly from Sk to T is strictly dominant for player K. Because then she will pay 1 over K, which is strictly smaller than at least 1 plus epsilon over K. Now, then delete this, delete the other strategy of that player, which is going to V and then from V to T. In the subgame 10, by deleting that other strategy, now player K minus 1 doesn't want to go to V and then to T, thereby playing at least 1 plus epsilon over K minus 1. It prefers to pay 1 over K minus 1 and go directly. So the strictly dominant strategy for player K minus 1 in this subgame is to go directly. And then we delete the other strategy of that player. So we delete the option to go to V and then to T, from V to T. So we inductively delete all those strictly dominant strategies which become successively strictly dominant when we delete more and more. And then we obtain a strictly dominant profile, which is of course unique, and that's of course the only Nash equilibrium, when everyone goes directly from her S to T. And the total cost is then 1 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over K. That's called the kth harmonic number, and that's approximately logarithm ln, the natural logarithm of K. So the price of stability, the ratio between the cost we may have to pay in the best, but there is actually unique Nash equilibrium here, which is the harmonic of K, and the best possible social welfare, which is 1 plus epsilon, the everyone goes through V, is arbitrarily close to this harmonic, so ln K, when epsilon is small enough, and epsilon can be taken to be close. So even the best equilibrium here can be arbitrarily close to ln of the number of players. And then we ask, what about the general Shaplin network design game? So we have seen two examples. In one example, we had an optimum Nash equilibrium, but also a bad one. In the other example, we had only bad Nash equilibrium, but the badness was logarithmic. So first of all, does every Shaplin network design game possess a pure Nash equilibrium? Because that's something we need for the notion of price of anarchy to make sense. And what is when there is Nash equilibrium, what is the largest price of stability which we may have? Because we have an example when even the price of stability is harmonic, or at least arbitrarily close to harmonic of the number of players. And actually the answers are, and I don't know whether we'll have time to prove it, that, and I do encourage you in your free time to read about that, but I don't know whether we'll do it in this course, that there always exists a Nash equilibrium, so there is no empty set of Nash equilibria in Shapley network design game. And as for the worst possible, so for the largest price stability of Shapley network design game with k plus, it's actually the harmonic of k. So this example is actually a worse example for price stability. Okay, that was the second application.